guys, and welcome back to my channel, Adisa Talks. So, sorry for being absent, but today we're actually going to talk about electrical transducers. And this is chapter 4 of my series, which actually talks about electrochemical sensors and semiconductor sensors. So, let's get started. Electrochemical measurements are determined through reduction and oxidation reactions that involve the transfer of electrons, which can be measured as electrical potentials. The measurements can be made through an electrochemical cells, which involve an electrode being placed in a salt solution called an electrolyte, and a charge separation is actually generated at the metal solution interface. This setup is called a half cell, and two half cells compose an electrochemical cell. As stated before, redox reaction actually allows for electrochemical measurements to be made. And a redox reaction is a chemical reaction that has a transfer of at least one electron from one molecule to the other. Some substances are actually capable of removing or transferring electrons. Substances that are allowed or capable of removing electrons are said to be oxidative or oxidizing and are called oxidants, while substances that are capable of transferring electrons are said to be reductive or reducing and are also called reductants or reducers. Usually, a galvanic cell or voltaic cell is a type of electrochemical cell where redox reactions take place. So, these cells actually have two electrodes that constitute of a pair of an anode and a cathode. The cathode is actually defined as an electrode where the reduction occurs, and the anode is defined as an electrode where the oxidation occurs. When the reaction happens, these actually indicate that the electrons move from the anode to the cathode, which shows that the current flows from the cathode to the anode. And an example of a cell, of a galvanic cell, that includes zinc and copper electrodes is the Daniell cell. Another interesting aspect of electrochemical measurement is determining the electrode potential. And this is determined through finding the direction of the current flow, which also depends on the ionization tendencies of the metals. With that, we can actually measure the relative potential of the metals by introducing a reference potential. And this reference potential could be a standard hydrogen electrode. There are different types of reference electrodes that could be used, such as silver-silver chloride electrode and a saturated calomel electrode. There are different measurements that could be obtained from an electrochemical cells. But something that you should know is that the electrode potential is dependent on the temperature and concentration of the analyte in the system. Thus, one piece of measurements that could be obtained is a Gibbs free energy, which is actually the work obtainable from the dynamic system at a constant temperature and pressure. Then the next piece of information that could be obtained is from the Nernst equation, which actually relates the electrode potential to the temperature and the standard state electrode potential, where you could determine the electrode potential based on the effective concentration of the oxidant and reductant and the chemical activity that's happening within the cell. The good thing about the Nernst equation is that it can be transformed to find, for example, the cell potential as well as the standard potential of the metal. One thing that should be understood is what happens when the electrode is immersed in the electrolyte solution. That is very important because when the electrode is immersed in the electrolyte solution, an interfacial region called a double layer is formed. And this double layer is actually two parallel layers of charges, where the first layer is made of ions that is absorbed on the surface of the electrode due to the chemical interactions that can either be positive or negative. And the second layer is actually formed by ions that are attracted to the first layer via Coulomb forces. So from there, the electrical properties of this layer actually affects the electrochemical measurements. And so when the potential of the working electrode is changed, the double layer actually acts as a capacitor which must be charged. Now, there are three types of electrochemical sensors. There are potentiometric sensors, voltammetric or amperometric sensors, or conductometric sensors. With potentiometric sensors, the electrostatic potentials are actually measured. And with these sensors, little to practically no current is involved in the measurements. In voltammetric sensors, the current measurement is involved. And with these sensors, potential of the electrode are actually held constant or maybe used as a variable input during measurements. And lastly, with conductometric sensors, resistance or maybe conductance is measured by alternating the current. A good example of potentiometric sensor is a pH sensor. In order to determine a voltammetric measurement called a voltammogram, a potential is actually varied or may be administered step by step to determine the current as a function of the cell potential. The applied potential actually drives the electron transfer reaction of the analyte. And also, sensors that use voltammetric measurements are glucose sensors that we'll actually review in a few sections. Glucose sensors don't only use voltammetric measurements, they could also use amperometric measurements because amperometric sensors measure the current response to detect the concentration of an analyte. And with glucose sensors, amperometric measurements can actually be used to determine the glucose concentration in a solution. As stated before, conductometric sensors or measurements measure conductance or resistance by alternating the current. And these measurements happen or are determined by using a sensing material that is specific to the analyte in question that is actually sandwiched between two contact electrodes, and the resistance of the entire device is measured. Now, one of the main advantages of conductometric sensors is the low manufacturing and cost, in addition to the fact that the preparation processes include skin printing, sputtering, and maybe evaporation. In a conductometric Urea biosensor, for example, photolithography is used to create interdigital electrodes that are used in the sensor. And when urea would bind to the urease, this will actually result in a change in conductivity between the electrode, which actually allows the sensor to detect a relative increase in the urea concentration. Another type of electrochemical sensors are capacitive chemical sensors. And these sensors are based on the measurement of changes in the capacitance. And the sensing principle behind the capacitive chemical sensor is that the absorption of a specific target molecule induces a relevant effect of changes in the dielectric constant and swelling. This then allows the impedance of the system to be measured. Another type of electrochemical sensors that I did mention a little bit at the beginning are glucose sensors. As you know, glucose sensors are used to measure the blood glucose concentration of a different patient, and they're kind of like important in managing diabetes, maybe type 1 or type 2 or even type 3. And because glucose sensors are usually characterized as amperometric sensors, they have a reducing property that allows current to be measured. And the current is actually measured through the generated enzymatic reaction that happens between the glucose, the enzyme, and the mediator. And in this reaction, the glucose reacts with the enzyme. The enzyme then reduces two mediators, and from there, through the oxidation process, the current is actually measured by the electrode. Pretty cool, right? Now, there are available commercially glucose sensors, and these glucose sensors work by maybe pricking the finger to draw the blood, and with a disposable test strip, the glucose concentration is measured. Now, let's move from electrochemical sensors and let's start talking about FET-based molecular sensors. Before talking about these sensors, I think it will be a really good idea to kind of discuss the basics of semiconductor semiconducting physics to kind of understand the mechanism behind these molecular sensors. And understanding the semiconducting physics include understanding electrical conductivity, resistivity, electrical field, as well as maybe current density. The basic parameters that are related to conductivity as well as electrical resistivity is Ohm's law. And Ohm's law is basically the electrical potential difference that is divided by the resistance of the material. And the resistance is actually proportional to the length and inversely proportional to the cross section of the specific material. This allows us to basically maybe determine conductivity, which is actually the inverse of resistivity. From there, we can determine maybe the electric field and also maybe the current density. Now, when dealing with a specific material, electrical conductivity as well as electrical resistivity, you're also dealing with charge carriers. And these charge carriers actually allow the electrical current to flow through electrical charges. And because through these charge carriers the current is actually induced, current density can be determined as well as maybe mobility, which is how quickly those charge carriers can move through the material, as well as maybe the conductivity as well as the resistivity of the electrons and the holes that make up these charge carriers. But the main idea behind these semiconducting devices is the control of carrier concentration by kind of introducing impurities or by maybe actively applying voltages or current. And these changes in the carrier concentration are actually utilized as the changes in the conductivity of the electrical devices for maybe different concentration to be determined. Now, one thing you may have noticed that I mentioned are electrons and holes that kind of make up these charge carriers. Now, these electrons and holes have an energy, and the energy band diagram actually represents the different energy levels and the internal statuses of these electrons and holes. Now, the valence band is actually a band that is made up of the occupied molecular orbitals, which are filled shells, and basically the electrons in this band are tightly bound together to the atom in the valence band, while the conduction band actually corresponds to the orbitals that allows the electrons to kind of move within the crystal structure or crystal lattice. Now, in a metal, the bands kind of overlap because there's always free electrons without excitation, while in a semiconductor device, electrons actually need to be excited to kind of move from the valence band to the conduction bands, while in an insulator devices, the band gap is pretty large because very few electrons can jump from one band to the other, which actually means that there's no current that flows inside. Now, a good representation of this energy band diagram is through an intrinsic semiconductor. And intrinsic semiconductors are actually semiconductors that do not contain impurities. Now, one thing that you should always remember and know is that both electrons and holes are actually free to move and carry electrical charges. But in order to know maybe the probability that this electron kind of occupies a state at energy is through the Fermic Dirac distribution function, which could also be called the Fermic level. And this level actually indicates how free an electron are distributed in an energy band diagram. Now, in FET molecular sensors, doping can be used. Doping is actually the introduction of impurities into a pure semiconductor crystal. There are two types of doping, a p-type doping and an n-type doping. A p-type doping is when a crystal is actually doped with atoms that can accept electrons, and these atoms are called acceptors. And the cool thing about a p-type doping is that the energy level of the unoccupied bonds are actually slightly higher than the valence bond and could be maybe easily thermally excited to occupy one of them than to go up to the bottom of the conduction band. Pretty cool, right? So in an n-type doping, on the other hand, the crystal is actually doped with ions or atoms that can be provided with one free electrons, and these atoms are actually called donors. For the n-type doping, these additional electrons from the donors can actually move to the conduction band and maybe raise the Fermic level. Now, when p-type semiconductors and n-type semiconductors are brought together, these are also called p-n junctions. And in these semiconductors, more electrons tend to travel from the n region to the p region than the other way around, and more holes tend to travel from the p region to the end region than the other way around. This local change in energy is called band bending. And an example of the mixture or the junction between p-type and n-type are called a p-n diode. And these are actually constructed based on the p-n junction or semiconductors that actually allows current to flow in one direction. There are other semiconductors that are actually out there, and this includes the MOSFET. The MOSFET is actually a metal oxide semiconductor field effect transistor. And this transistor is actually used for the amplification and the switching of electrical or electronic signals. It is actually usually consists of three terminals, which are maybe the source, the gate, and the drain. The cool thing about the MOSFET is actually it utilizes silicon oxide as an insulator, which is actually the main reason why it's called a MOSFET. Now, the MOSFET actually has different conditions. In a flat bend condition is when there is no voltage that is applied to the gate and the FEMIC level are actually equal. And so the p-n junction at the source body and the drain body interfaces which actually prevents the current flow in either direction. In the accumulation condition, there's no current that flows between the source and the drain. And that's because there is the accumulation of charges which actually occurs on both sides, where the electrons actually move to the metal side and the holes actually move to the semiconductor side. In the depletion state or condition, there is still no current that flows, and that's because the charges are depleted on both sides of the metal and on the semiconductor. Lastly, in the inversion condition, the electrons in the body are actually attracted to the surface on the gate insulator, and with this attraction, there is now the conduction between the source and the drain that is allowed. Pretty cool, right? Now there are P MOSFET and N MOSFET, and with P MOSFET, actually a thin layer is formed on the P channel, and this allows basically conduction to occur as stated before between the source and the drain. A device that includes both P MOSFETs and N MOSFET on a single chip are called a Cosmo device, which is a complementary metal oxide semiconductor device. And the cool thing about these devices is that they actually use a standard silicone process as part of their fabrication. Now, the good thing about these silicone is that they're actually used or could be used for chemical as well as biomedical sensing. And that is basically they can be easily modified and maybe insulated for these different practices. Now let's move on to organic transistor-based sensor. And these sensors are actually based on organic and polymeric FET that is basically a new region of research because organic chemicals can form a really great chemical interactions with various analytes. Now, because organic thin film transistors actually are composed of a thin film of organic semiconducting material, they're actually categorized into two types, which are mainly the organic field effect transistors and the organic electrochemical transistors. The OFETs, or the organic field effect transistors, actually utilize field effect doping, where the carrier density in the organic semiconductor is regulated by the electric field from the gate electrode across the insulating layer. But the OECTs, which are the organic electrochemical transistors, they actually utilize electrochemical doping. And this is where the conductivity of the organic semiconductor is controlled by ions from the electrolyte. Now, there are also other types of FET sensors, such as maybe nanowire-based sensors. And these sensors are pretty much of interest right now because they're very sensitive and they have really great electric properties, which could be good for different electrochemical sensing or biological sensors. And a good example of a nanowire sensor could be a silicone nanowire sensor. And with this sensor, the nanowire is actually connected to two electrodes which actually measure the conductance. In one of the applications, the nanowire can actually be modified to undergo protonation and deprotonation of a specific molecule or protein. And this change in the surface charge actually allows the FET to detect the change in maybe the pH based on the change in the surface charge. This actually allows conductance and maybe pH measurements to be made using the sensor. Now, these silicone nanowire sensors can actually be fabricated by using the top-down approach that I kind of talked about in chapter 2 or 3 of my series. So check it out if you want to know a little bit more. But there are different other types of nanowire sensors that have evolved, such as a polymer nanowire FET sensor. Now, based on the different applications, you can maybe choose if you rather have a silicone nanowire sensor or a polymer nanowire sensor. Now, the other sides of electrochemical sensors include using maybe carbon nanotubes and maybe graphene to make sensors. So let's talk about it. Carbon nanotubes can actually be used to make molecular sensors, and that is because of the unique material and the different property that gives us this unique geometry that can allow for pretty cool sensors to be made. There are also a single wall nanotubes as well as a multi-wall nanotube. And the single wall carbon nanotubes have a diameter of about 1 nanometer that can contain a different geometric shape depending on the direction, while the multi-walled carbon nanotubes have about a thicker diameter, which also depends on the geometry as well as the direction. Now, some of these sensors have actually been used to detect gaseous molecules, or maybe the conductance of a specific molecules that maybe can drastically increase or decrease. But the cool thing and the great advantage and characteristic of using carbon nanotubes for molecular sensors or sensing include that they have a really small dimension and have a really high surface volume ratio or rate, which allows for more molecules to be detected, more chemicals to be detected, or maybe more neurotransmitters to be detected, or glucose concentration to be detected. Now, even though carbon nanotubes are amazing, let's not neglect graphene. Now, graphene is a pretty interesting material which has a different atomic structure, which has been quite studied in terms of strengths and mechanical exfoliation to kind of produce very thin symbols for molecular or electrochemical sensing. Some of the cool properties of graphene is basically that it has a really high mobility, which actually exceeds carbon nanotubes. That's pretty awesome, right? And this combination of the great electron mobility as well as a great charge transport, which kind of gives graphene quite good properties for electrochemical or chemical sensors. That's pretty cool, right? And with graphene-based gas sensors or glucose sensors, different changes in resistivity or maybe voltages can be measured, and maybe a voltammogram could be actually determined to see how these graphene-based sensors are actually able to detect these different molecules or gases. Alright guys, I hope that this chapter was very much insightful and you guys were able to learn about graphene sensors and modified sensors and carbon nanotube sensors. So, see you next time in the next chapter.